Hi everyone and welcome to today's video. So today I'll be introducing to you how to integrate trigonometric functions. How do you integrate all these trigonometric functions? Let's find out in today's video. Alright, so today we're going to see how to integrate trigonometric functions. How is that going to work out? So let's look at it. So if we consider integration as the reverse process of differentiation, then the following illustrate the way in which trigonometric functions can be integrated. So look at this table right here. So you remember that whenever we actually differentiated sine x, we actually got a cos x, and then whenever we differentiated so as you can see here, whenever we differentiate sine x, we actually get a cos x. So that's why in reverse, moving back, we actually get a, so if we move back from integrate a cos x, we get back the original sine x. But we also remember that whenever we actually differentiated the cos x, so remember whenever we used to differentiate cos x, the answer would be negative sine x. So that actually means that if we integrate negative sine x, it is what gives us the original cos x. But in a case where we have to integrate a positive sine x, it means that this time we shall actually have a negative cos x. So that's actually the difference right there. And then we also remember that whenever we differentiated tan x, we also used to get a sec squared x. So definitely, when you integrate sec squared x, we get tan x. So also, otherwise, when you also integrate cosec squared x, we get negative cot x plus c. Then also, we remember that whenever we whenever we differentiated a positive cosec x, we actually got a negative cot x cosec x like that. So that means that if we are integrating now a positive cot x cosec x, it means that now the antiderivative will be a negative cosec x plus c. And then we also remember that whenever we differentiated a sec x, we also always got a sec x tan x. So now if we integrate a sec x tan x, we actually get a sec x. So it's the same like that in reverse. Alright, so now we can also look at the cases where we actually have the inverse trigonometric function. So you remember that whenever we differentiated tan inverse of x, we always got this. We always got 1 over x squared plus 1. And whenever we also differentiated sine inverse of x, we got 1 over root of 1 minus x squared. Then also, whenever we differentiated cos inverse of x, we also got negative 1 over x squared plus 1. So now in this case, whenever we integrate these, we actually now can go back to these as we actually see in the table. Alright, so let's look at some questions. This will allow us to understand this better. So you're given a question and you're being told to integrate sine 2x. So this is actually an example of a double angle. So this is not direct, so you may not see it, but this will actually require a u-substitution. So what we're going to do is we're going to let u to actually represent this 2x right there. And then when you differentiate this, we get du dx as being equal to positive 2. Then we're going to make dx a subject and dx shall be equal to du over 2. And then therefore if we put this back, we'll have sine u times du over 2, as you can see right there. Now you can actually say that we can actually extract out a positive half into the integral of sine u. And remember that the integral of sine u is negative cos u, as you can see right here. So we have a half negative cos u plus c. So we have negative half cos u plus c. But remember that u was equal to 2x, so therefore our answer is negative a half cos 2x plus c. And that's the answer. Alright, so let's move on to question number 2. So question number 2, we're being told to evaluate the integral of tan x dx. So how do we do this? So now this is not as straightforward. So because we're going to have to first convert that tan x into sine x and cos x. So this is what we're going to do. Remember, tan x is actually sine x over cos x dx. And now the next thing we're going to do is we're going to include u substitution. And why are we going to do that? It's because somewhere along the way, if we, for example, make u to be equal to cos x, if we differentiate that, we'll actually have an element of sine x somewhere. So that's why this is actually going to work out with u substitution. Now let's look at how that works. So we're going to let u to be equal to cos x. And then we can say du dx is actually negative sine x. So I think you see what I actually mean. So there's an element of negative sine x appearing, which hopefully will cancel out with the sine x and will easily solve this number. So if we make dx subject, dx shall be equal to du over negative sine x. Then we're going to substitute everything back in, and what shall we have? So where there is cos x, remember we've placed that as a u, and then we have sin x times this value right here. Now what we're substituting this for where we have dx. So when we do that, we can see that this and this shall cancel, and then what we'll be left with is a negative into the integral of 1 over u du. And now this is actually easier to work with because the integral of 1 over u, from our knowledge of exponentials and natural logarithms, is going to be equal to ln u. So we have a negative ln u plus c. But remember that u was cos x, so we're going to substitute that back in. So we have a negative ln cos x plus c. But from properties of natural logarithms, we know that this negative right here can be made a power of this value of cos x. So it can actually be converted into ln cos x to the power negative 1. Of course, that means ln 1 over cos x. But from trigonometry, we know that 1 over cos x means sec x. So basically, in the most simplified version, this question has an answer of ln sec x plus c. And that is the answer. Alright, so question number 3, we're being told to evaluate the integral of cot x dx. Now this is another easy one. Now this basically we're also going to convert in the form of cos and sine. So remember that cot x is actually cos x over sine x dx. We can already see that if we make u, if we use u substitution and make u to be equal to sine x, there's actually an element of cos x that we shall also find in this one. So let's do that. So we've let u to be equal to sine x, and you can clearly see that du dx is equal to cos x. So I think you see what I mean. So if we make dx the subject, dx shall be equal to du over cos x. So let's plug in that back, and this is what we have. So you can see where we have sine x, we place a u, and then we have cos x over u times. So we can say that where there was dx, we replace that with du over cos x. So that's why we have that. So we can say that cos x and cos x will cancel. And what shall we be left with? The integral of 1 over u du. And we know that from the knowledge of exponentials and natural logarithms, the integration, we know this shall be ln u plus c. But remember that u is actually sine of x. So we put that back in, and we can have our final answer as ln sine x plus c, and that is the final answer. So question number 5, we're being told to evaluate the integral of sec x dx. Now this one is quite more complex than the other numbers that we've been doing before, because here there is no straightforward way, but we're going to have to use a unique kind of u substitution in this case, but it's actually doable. So for this case, we're going to multiply and divide the integrand with sec x plus tan x, and that is because only these can actually bring out something in u substitution that will cancel out with the value that we actually have up here. But you understand it as we work it out. So just know that this has properly been researched on, and it has been confirmed that this is the best way to handle this. So we'll always multiply and divide the integrand with sec x plus tan x. So this is what we have. So we've multiplied the integrand, so we've multiplied it with sec x plus tan x at the numerator and at the denominator. So this is what we have right here. Now basically, because it's like this, it means we've not changed the meaning, because this and this can actually cancel and we'll be left with sec x. So we've not changed the meaning of the question. So this is actually okay. Now we can actually clearly see that we can multiply this sec x inside these brackets, and we'll have sec squared x plus sec x tan x. And now that we have this, we can actually now get a value that will actually cancel out with something in the numerator. So now clearly we can now let u to be equal to sec x plus tan x. So du dx shall be equal to, so actually we've let u to be equal to this numerator value, which is sec x plus tan x. So we can say du dx shall be equal to, so the derivative of sec x is sec x tan x, and then the derivative of tan x here is sec squared x. So we have sec x tan x plus sec squared x. And then if we make dx the subject, dx shall be equal to du over sec squared x plus sec x tan x. And this will work, and you can say this clearly is going to cancel out with what we have at the numerator. So now we plug everything back, we can say this will actually work for us. So this will actually cancel with that, and we'll be left with the integral of 1 over u du. So this is the best way to actually work out this number. So the integral of 1 over u is going to be ln u plus c. But remember that u is sec x plus tan x. So therefore our final answer is ln sec x plus tan x plus c. So this is how we solve the integral of sec x. Alright, so next we're going to also evaluate the integral of cosec x dx. Now this is quite similar to the former number that we've actually just done, because there is no direct way, so we actually have to use a unique u substitution. So in this case, we're going to multiply and divide the integrand with cosec x minus cot x. So this has also clearly been researched on, and this is the best way to work out this integral. So just trust me in this case. Alright, so we're going to multiply we're going to multiply this one by this. So we multiplied and divided it by this integrand right here. So at the top we have this times cosec x minus cot x over cosec x minus cot x. Now, as I've said before, this does not change the meaning because this and this can cancel and we'll be left with cosec x. So it's basically correct. Alright, so let's open brackets. So in open brackets, we'll have cosec squared x minus cosec x cot x. Now, what I can already see is when I actually make u to actually be this denominator value, I'll get a value that will cancel out this numerator, and that's how I'll know that this works. So I'm going to let u to be equal to cosec x minus cot x. So du dx shall actually be equal to, so the derivative of cosec x is negative cosec x cot x, and then the derivative of cot x right here shall be equal to cosec squared x, but it shall actually be the negative. So now it will affect this sign and we'll have a plus, and that's why we have it like that. So if we make dx the subject, dx shall be equal to du over cosec squared x minus cosec x cot x, as you can see right there. Now we can actually rearrange this into cosec squared x minus cosec x cot x. So that actually doesn't change the meaning. So when you put that back in, we can actually see that this and this will cancel, and then we'll be left with the integral of 1 over u du, and then ln of u shall be equal to, so actually our answer shall be equal to ln u plus c. So we'll all have to remember is u is cosec x minus cot x, so we're going to put that back, and then our final answer shall be ln cosec x minus cot x plus c. Alright, so moving on to the next question. So next question, we're being told to evaluate the integral of x cos x squared dx. Now this is another unique one. So this will also require u substitution, as I can already see. And what kind of use? Why are we going to use u substitution? I can already see if I actually make u to actually be equal to this x squared right there, then that derivative of x squared shall be equal to 2x. And then I can see that that x somewhere along the way will cancel out with this x, and then we shall be able to solve this question. So let's see how that will work. So this is what we have. So we're going to let u to be equal to x squared, and then du dx shall be equal to 2x, and then if we make dx subject, dx shall be equal to du over 2x. So I think now you're getting the point. So we're going to put that back in. Then I can see now that I'll have x cos u times du over 2x. So I can already see that this x will cancel that x, and then I'll be left with only u values. So once I'm left with only u values, I can set, I can actually pull out a half. So I have a half into the integral of cos u. So this is actually now very doable. So the integral of cos u, remember, is actually sine u. So I'll have a half sine u plus c. But remember that u is x squared, so therefore our answer is a half sine x squared plus c. And this is how we solve this number. Alright, so let's look at another one right here. So we're being told to evaluate the integral of sine x into bracket 4 cos cubed x plus 6 cos squared x minus 8 close that bracket dx. So this looks scary at the very beginning, but it's actually an easy number also. So what are we going to do in this case? So what we're going to do is we can actually see that there is actually cos in common. So there is cos here, there is cos here, and then there is always a relationship between cos and sine. So we're going to let our u to be equal to cos x, and then we know that this is the more complex part, this value inside the bracket. So we're going to let something from this bracket right here, and we've chosen to let it be cos x. And surely when you differentiate cos x, somewhere along the way we'll actually get a value that will cancel out this sine x, and that's how I know this will work. So du dx shall be equal to negative sine x. I think you can already see the point. And then dx, if we make this subject, dx shall be equal to du over negative sine x. So substitute that back in, And as you can see, wherever there was a cos, we've actually replaced that with a u. And then I can already say that this sine x and this sine x shall cancel, and then I'm assured that I'll only be left with values that are in terms of u. So as you can already see here, this negative will be pulled outside, and then this is why we have it right there, and then sine x and sine x shall cancel. So this is what we're left with right now. So now whatever is inside the integral can now simply be integrated. Now we know that the integral of now 4u cubed shall be equal to, so we shall have 4 over 4u power 4 plus, so for this value here 6u squared shall become 6 over 3u cubed, and for this we'll have 8u, then plus c. But remember there is also a negative right there. So we're going to plug in the negative, and you can actually see that this sign will change. So I'll have a negative here, and this will become a plus. So I'll have negative u power 4, because this and this become 1, minus 6 over divided by 3 is 2, minus 2u cubed plus 8u plus c. But remember that u is cos x, so therefore our final answer is negative cos power 4x minus 2 cos cubed x plus 8 cos x plus c, and that is our final answer. Alright, so question number 8, we're being told to evaluate the integral of e2x plus sec 2x tan 2x dx. Now I can already see something very much in common. I can already see that there is 2x coming up everywhere, so I can already see what we actually have to deal with in this case. So what we're going to do is we're going to let u to actually be equal to that 2x, and you can already say this is the more complex part of it, so we're going to let 2x because it's going to help us out. So we remember du dx shall be equal to 2 when we differentiate this, and then if we make dx subject, dx shall be equal to du over 2. So we can already say that everything right now is already in terms of u. So I have the integral of eu plus sec u tan u times du over 2. So I can already say that I can pull out a half, and then this is what it will actually look like. Now these are actually easy to integrate, so this can easily be integrated, and this can also directly be integrated. So now the integral of eu is eu, and then the integral of sec u tan u is actually sec u. And that is because whenever we differentiate sec u, we get sec u tan u. So this is actually what we get. But remember that u is 2x, so therefore our answer is a half times e2x plus sec 2x, close that bracket, plus c. And that's the answer we're looking for. Alright, so next question is question number 9, and we're being told to evaluate the integral of 2 cos x minus sin x over 2 sin x plus cos x dx. So what do we do here? So we can already see that there is actually going to be a relationship between the denominator and the numerator. So usually everything that is in terms of sine and cos usually actually have some form of relationship. So we're going to let u to actually be equal to this value right here at the denominator. So when you do that, we can actually see that du dx shall be equal to 2 cos x, because the derivative of sine x is cos x, and then the derivative of cos x right here is negative sine x. So that's why we have a minus sine x. So this sign changes. So we have 2 cos x minus sine x. So if we make dx the subject, dx shall be equal to du over 2 cos x minus sine x. So you can already say that we made the right choice, because this will clearly cancel out with that numerator. So plugging everything back, this is what we have. So this and this will cancel, and then we'll be left with the integral of 1 over u du. So we'll also know the integral of 1 over u is ln u plus c. And then we remember that u is actually 2 sin x plus cos x, as we've actually stated right here. Then our final answer shall be equal to ln 2 sin x plus cos x plus c. And that is the final answer. So question number 10, we're being told to evaluate the integral of cos 4x minus cos 2x over sin 4x minus sin 2x dx. So this looks complex at the very beginning, but it's actually an easy one. So how are we going to do this? So we're going to first remember something from factor formula. Now you can already see that these are double angles, and these are actually very big. So these are actually scary for some people when they look at them, but factor formula actually help us simplify these a little bit. So from factor formula, remember that when we have a cos minus cos of different angles like that, we can actually change it and it will become negative 2 sin x. So factor formula is actually a formula in trigonometry that we can actually apply. So this will become negative 2 sin into 4x plus 2x over 2 sine 4x minus 2x over 2. And then at the denominator, where we have sine minus sine, we will have 2 cos 4x plus 2x over 2 sine 4x minus 2x over 2. So when you simplify that further, 4x plus 2x is 6, so 6 divided by 2 is 3x. And then 4x minus 2x is 2x, 2x divided by 2 is x. And then 4x plus 2x here is also 6, 6 divided by 2 is 3x. Here 4x minus 2x is 2x, 2x divided by 2 is x. So this is what we end up having right there. Now I can already see that some values here will cancel. This 2 and this 2 will cancel. And then I can already see that this sin x and this sin x will cancel. So I'll be left with the negative sine 3x over cos 3x. Now, I can already see that there's actually going to be a relationship right here. So what I'm going to do is I'm going to let u to actually be equal to this cos 3x, because there's always a relationship between a cos and a sine. So now du dx shall be equal to, so when I actually differentiate this, du dx shall be equal to negative 3 sine 3x. Then if I make dx subject, dx shall be equal to negative du over 3 sine 3x. So when I plug that back in, this is what I'll have. So I can already set up a value that will actually clearly cancel out with that sign right there. And then I'll be left with a third into the integral of 1 over u. Now I can already see that this negative will actually affect this negative, so I'll only have positives left. So I have a third into the integral of 1 over u, of which we know that the integral of 1 over u is ln u. So we have a third ln u plus c. But remember that u is cos 3x, so therefore our final answer shall be a third ln cos 3x plus c. So question number 11, we'll be told to evaluate the integral of sine 2x over 1 plus cos 2x dx. So what do we do in this case? So this is what we have. So we're being told to integrate this. Now first of all, what we can do as the first step is we can clearly see that we will have to first convert everything into simpler angles. Now these are both in terms of double angles, but remember that sine 2x is 2 sine x cos x, and then we remember also that cos 2x can actually be expressed in terms of, so there are two ways you can express cos 2x. It can actually be equal to 1 minus 2 sine squared x, or 2 cos squared x minus 1. So these are two forms in which cos 2x can actually be replaced, but we actually have to choose one that is going to be used for us in this case. Now you can already see that we actually have a positive 1 right here. Now I can see that if I was to actually use this first format right here, I would have this 1 adding this 1, and then it would become a 2, and that is not useful for us in this case. Actually, it may actually work for us later on, but actually we want something quicker. So I actually chose to use this one right here. I feel this one will actually easily, the ones will actually cancel with each other, and I'll have and be able to move straight forward. But in a way, the upper one would also have worked, but this second one, 2 cos squared x minus 1, will actually be quicker for us. So this is what we have. So I can already see that this one and this one will cancel, and I'll be left with 2 cos squared x at the denominator. And then I can see that this and this reduce, and I'll be left with 2 sine x over 2 cos x, of which the 2's also cancel, and I'll be left with the integral of sine x over cos x dx. Now this can actually be solved with u-substitution, because there's a relation between sine x and cos x. So I can actually let u to actually be equal to cos x, and then du dx shall be equal to negative sine x. So if I make dx subject, dx shall be equal to negative du over sine x. So therefore, what I'll have is the integral of sine x over u times this negative du over sine x. So this and this cancel, and I'll be left with the integral of negative 1 over u du. So this is what we have. So remember, the integral of 1 over u is ln u, so I have negative ln u plus c. But remember that u is cos x, so therefore I have negative ln cos x plus c. But remember that from the properties of natural logarithms, this negative can be made a power. So I'll actually have this cos x to the power negative 1. And then therefore that is the same as 1 over cos x, which is actually sec x. So I'll have ln sec x plus c. So there are cases where you actually just have to, it's actually neat to actually simplify to the simplest format, of which now I'll have ln sec x plus C, and that is the answer that they wanted. So question number 12, we're being told to evaluate the integral of, so that we have limits, so the upper limit is pi over 2, and then the lower limit is 0. And then we have cos x over 1 plus sine squared x dx. Then we're being told to put this correct to 3 decimal places. So this is actually an easy one to solve, and this is what we have. So I can already see that there is a relationship between there's a relationship between sine and cos. Now in this case, I can actually let the u to actually be equal to sine x, and that will actually cancel out that numerator value. So if I let u to be equal to sine x, du dx shall be equal to cos x, and then therefore if I make dx subject, dx shall be equal to du over cos x. So if I substitute that back in, I can already see that now I can actually eliminate that numerator value, and then what I'll be left with is the integral of 1 over 1 plus u squared du. But now if you remember something from the derivatives of if you remember something from the derivatives of arctan, so remember that when you differentiate tan inverse of x, for example, it is equal to 1 over 1 plus x squared. And then remember that if I integrate this, it is like reversing, and it will take me back to that tan inverse of that. So that depends on the variable that we choose right there. But now this is a case where the variable is actually u. So basically the integral of 1 over 1 plus u squared is actually going to be equal to tan inverse of u, as you can see right there. But we actually have the upper limits and the lower limit. But now before we do that, we'll actually have to put everything back in terms of the original variable x. So remember that u is actually sine x, so now we have tan inverse of sine x, and then to those limits pi over 2 and 0. So now we can plug in the limits. Alright, so basically sine pi over 2 shall actually be equal to 1, and then sine 0 is 0, so 0 times this is 0, so this whole part cancels out. So I'm left with tan inverse of 1. So put your calc in radians and you'll get your answer as 0.785, and that is the answer that they wanted, because they wanted to correct 3 decimal places. So this is what we have. Alright, so question number 13, we're being told to evaluate the integral of 10x plus 3 over x squared plus 16. So how are we going to do this in this case? So this is actually an easy one also. So when I look at this question here, I can already see that this can actually be split into 2 different separate fractions, because I have 10x plus 3 at the numerator. So this can actually be split as the integral of 10x over x squared plus 16 dx plus 3 over x squared plus 16. So when I actually do this, we can actually now work on both of them separately. So now I can already see that this side here, I can straight away use u-substitution. So let's deal with that first. So I'm going to let u to be equal to x squared plus 16, and then du dx shall be equal to 2x. So if we make dx subject, dx shall be equal to du over 2x, of which if I put that back in, I can actually see that this and this will cancel. Then 10 divided by 2 is 5. So I'll actually have a 5 right there. So I'll have a 5 over u. I can pull out the 5 and we'll have 5 times the integral of 1 over u du. But remember the integral of 1 over u is ln u. So I have 5 ln u plus c. But remember that u is x squared plus 16. So therefore I'll have 5 ln x squared plus 16 plus c. And now let's deal with the other side. So how about the integral of 3 over x squared plus 16 dx? So how do we solve this one? So now the first step we're going to do is we're going to actually factorize out the 16. And so that I'll actually have 16 into x squared plus 16, x squared over 16 plus 1. Now the reason for this is actually I remember something from the knowledge of tan inverse of something being equal to 1 over 1 plus x squared. So actually it means that what we actually have here actually has to be squared. So we're going to use the knowledge of that. So in this case, I can actually factorize everything out, and then I can actually see that if I factorize out 16, I'll remain with x squared over 16 inside plus 1. And then I'll have 3 over 16, and I can pull that out of the integral. So now inside here, I'm left with 1 over this. So I'll have x squared over 4 squared, then plus 1. Now the good thing here is that 16 is actually the same as 4 squared. So this can be expressed as 1 over x over 4, then square both of them plus 1. So this format can actually also be put in terms of tan inverse when we actually integrate it. But now the difference with all the other values is now instead of having tan inverse of, so instead of it becoming tan inverse of x or tan inverse of u or something, we'll actually have it being as equal to tan inverse of this value that we actually have right here inside the bracket. So now this shall become tan 3 over 16 tan inverse of x over 4 plus c. So now if we combine everything, the final integral shall be equal to, so this integral to initially given shall be equal to this value here, 5 ln x squared plus 16 plus this 3 over 16 tan inverse of x over 4 plus c, and that is the answer that they wanted. Alright, so question number 14, we're being told to evaluate the integral of sine inverse of x over root of 1 minus x squared dx. Alright, so when I actually look at this question here, I can already say there is actually a relationship between this sine inverse of x and then this root of 1 minus x squared. And that is because I know that when I differentiate sine inverse of x, I actually get 1 over root of 1 minus x squared. So I actually see a relationship right there. So that means I'm going to let that numerator actually be equal to u. So I'm going to let u be equal to sine inverse of x, and then therefore du dx shall be equal to 1 over root of 1 minus x squared. So let's make dx subject, dx shall be equal to du times root of 1 minus x squared. So when you plug that in, we'll actually have something that looks like this. So where there is sine inverse of x will actually place a u, then I can actually see that this and this will cancel, and hence we've actually made the wise decision. So we can see that there are no more x's and everything is in terms of u. So now we're finding the integral of u du, which is actually equal to a half u squared plus c. But remember that u is sine inverse of x, so therefore we plug that back in and we'll have a half into bracket sine inverse of x, square that bracket plus c, and that is the answer to this question. Alright, so next we're looking at a question from UNEB chapter 2012, and this was question number 7. So being told to evaluate the integral of, so at the numerator we now have sine inverse of 2x over root of 1 minus 4x squared dx. So how do we solve this? So same to the former question, there is actually a relationship between this value at the numerator and then the value at the denominator. And that is because when I differentiate this, I'll actually have a value that is actually similar to that in a way. So I'll actually have 1 into 1 over 1 minus a value that is actually related to that. So I'll actually have 2x squared. But then let's look at how that will work. So I'm going to let u be equal to sine inverse of 2x, and then when I differentiate that, I'll actually get 1 over root of 1 minus 2x into bracket squared. So if I make dx subject, dx shall be equal to du times 1 over 1 minus 4x squared, because when I square this, I'll actually get 4x squared. Alright, so we can plug that in, and therefore we'll have, so where there was sine inverse of 2x, I actually placed a u, and then it's u over root of 1 minus 4x squared times, so now where there is dx, we're going to substitute it with this, so times du times root of 1 minus 4x squared. So I can actually see that this and this cancel, and then now everything will be in terms of u. So I'll have the integral of u du, and then therefore the integral of u shall actually be equal to a half u squared plus c. But remember that u is actually sine inverse of 2x, so therefore we plug that back in and we'll have a half into sine times sine inverse of 2x, close that bracket, squared plus c, and that is the answer to this question. Alright, so let's move on to another section of trigonometric integration. So now we're looking at cases where we have to find the integral of product of two sines, two cosines, or a sine and a sine. But in this case, we're going to look at those cases where there are actually double angles involved. So there are no squares in this section. So looking at those cases where there are actually double angles that are actually multiplying themselves. So we're saying that the product of two sines, two cosines, or a sine and a cosine can be integrated by first expressing the product as a sum or difference of trigonometric functions by use of factor formula. So let's look at the examples that I mean. So imagine you're given a question like this. Evaluate the integral of 2 cos 3x cos x dx with respect to x. So someone looks at this question and they're actually scared. But this is actually an easy one. So factor formula is going to help us solve such a question. So this is what we have. So we're going to consider the following factor formula identity. So do you remember that from factor formula that whenever we had cos A plus cos B, it actually gave us a value that was actually 2 cos A plus B over 2 cos A minus B over 2. And why was that? It was because this is actually what gives us something that is in terms of product of cos and cos. So that's why we're looking at a case where we have cos A plus cos B, and that is because here we have a cos multiplying a cos. So when we're having a case where a cos is multiplying a cos, so in a case where a cos is multiplying a cos, that comes from the factor formula cos A plus cos B. So this is the factor formula that we're going to consider for this case. So now if we compare the two, let's compare this value right here. So we're going to compare this to actually what we have right there. So we can actually see that this value A plus B, is equal to 3x. So we have A plus B over 2 being equal to 3x. So if we make A plus B the subject, we should have A plus B being equal to 6x. And then this is going to be equation 1. So we can also see that A minus B over 2 should actually be equal to x right there. So if we make A minus B the subject, we have A minus B being equal to 2x, and that shall be equation 2. Alright, so for the first step, we're going to add equation 1 to equation 2, and what we'll get is 2A being equal to 8x, and then A shall be equal to 4x. And then next, we're also going to get equation 1 minus equation 2, and we'll get 2B being equal to 4x, of which B shall be equal to 2x. So once we've done that, we can actually see that therefore, now that we actually know what A is and what we know as B, what we know B being equal to, so now we can actually substitute into that other equation that we actually have initially. So remember that we had actually said that cos A plus cos B was actually going to be equal to what we are actually solving. So now we can actually substitute into this part right here. So where there is an A, we shall put the value we get, and where there is a B, we put in the value that we got. So that's why we have cos 4x plus cos 2x shall actually be equal to what we actually had derived. So this is actually what we need. So this shall be easier to integrate. So the integral becomes the integral of 2 cos 3x cos x dx shall be equal to the integral of cos 4x plus cos 2x dx. So let's integrate this. We can actually see that now the integral of cos 4x shall actually be equal to a quarter sine 4x, and then the integral of cos 2x shall actually be equal to a half sine 2x plus c, and that is the answer that they wanted. Alright, so next we're being told to evaluate the integral of cos 3x cos 5x dx. So how do we solve this? So first of all, we can actually say this is a product of cos, and then if you consider the factor formula of this, remember that now it comes from cos A plus cos B being equal to 2 cos A plus B over 2 cos A minus B over 2. So now let's compare these. Now as we compare these, we can actually see that now in this case there's actually a not 2 right here as we compare. So that means this is actually slightly different. So now we're going to actually move these 2 away from here so that we actually have something better to can actually compare with. So now we can actually see that if we divide 2 on both sides, we'll have a half cos A plus cos B being equal to cos A plus B over 2 cos A minus B over 2. So now this is actually now we can now actually now directly compare this to what we actually have right there, because now there is no 2 involved. But now every single time we actually work on such numbers, I always encourage you that the value that you compare to A plus B over 2 should actually be the bigger of the 2 values, because that actually doesn't change the meaning. So we're going to let that first section be actually be equal to 5x, and the other section should actually be equal to 3x. So we're going to rearrange that a little bit. So now we're going to compare this value right here with cos 5x cos 3x. So you can actually say I've actually rearranged this, but it actually doesn't change the meaning, but it will actually be easier if you actually equate the a plus b over 2 to actually the bigger value. So now a plus b over 2 shall actually be equal to 5x, and then if I make a plus b the subject, a plus b shall actually be equal to 10x. Then a minus b over 2 shall actually be equal to 3x, and then if I make a minus b the subject, it shall actually be equal to 6x, and that shall be equation 2. So now we shall have equation 1 plus equation 2, which shall actually give us 2a being equal to 16x, and then a shall actually be equal to 8x. Then I'm also going to get equation 1 minus equation 2. So now this is the most important reason why actually I make the first part the bigger one, because in this subtraction I actually want to avoid negatives. So we shall actually get 2b being equal to 4x, of which b shall actually be equal to 2x. So now when I substitute all those back into our integral, so now wherever there is a, I actually put 8x, and wherever there is b, I actually put 2x. So now this shall now actually be equal to cos 5x cos 3x. So now this is what we can actually use to represent that. So now the integral then becomes, so the integral of this shall actually be equal to a half cos 8x plus cos 2x dx. So I can actually say I can actually pull the a half out of that, and then I have a half into the integral of cos 8x plus cos 2x dx. So now both of these can actually be solved using u-substitution individually, where we actually let u to actually be equal to this, and then this can actually be u. So in the first example in this section, I actually showed you how to integrate double angles. So when you actually integrate both of them, you'll actually get, for this I'll actually get 1 over 8 sine 8x plus, and for this I'll get a half sine 2x, then plus c. So actually I can multiply the half inside, and then I'll have 1 over 16 sine 8x plus a quarter sine 2x plus c, and that is our answer. So question number 3, we're being told to evaluate the integral of, so this is actually now a definite integral, where the upper limit is pi over 3, then the lower limit is 0 to sine 3x cos x dx. So now we actually have a sine multiplying a cos. So when we consider factor formula, so the factor formula we're going to consider this time is sine a plus sine b, because this is actually what gives us a product of a sine and a cos. So sine a plus sine b, we know from factor formula, is equal to 2 sine a plus b over 2 cos a minus b over 2. Now we have a 2 here, so that means this can actually be compared directly. Alright, so now we compare. So we'll compare this. So now we'll have this value right here compared to that value right there. And now I can see that this is already okay, because this is the bigger value and this is the smaller value. So I always say it's better to compare the bigger value with that. So now we can let a plus b over 2 be equal to 3x. As you can already see, that's what happens when you compare. Now a plus b shall actually be equal to 6x. This shall be equation 1. And then we can also say that a minus b over 2 shall actually be equal to x, of which a minus b is equal to 2x. So equation 1 plus equation 2 shall actually give us 2a being equal to 8x, of which a shall actually be equal to 4x. And then if I get equation 1 minus equation 2, I'll have 2b being equal to 4x, and then b shall actually be equal to 2x. Now the reason I do this, now the reason we don't have any negatives here is because I actually chose to equate this to the bigger value, and I encourage you to always do that every single time. So therefore we will have sine 4x. So now we have sine 4x. So where there is a, we actually put 4x, and where there is b, we actually put 2x. So sine 4x plus sine 2x shall actually be represent this value right there. So now the integral becomes this. So now this is the simplest way to actually integrate this. So now we know that the integral of sine 4x is actually going to be equal to negative a quarter cos 4x. So this you get actually using u-substitution, where you let u be equal to 4x. So you actually get negative a quarter cos 4x plus, then here you get negative a half cos 2x. But remember the actual limit, so the upper limit is pi over 3 and the lower limit is 0. So when you plug in the limits, this is what we actually have right now. Now right here we can actually see that cos of 0 is 1, so we'll have 1 right there. This shall also be equal to 1. And then we can actually see that cos 2 pi over 3 shall actually be equal to negative a half. So when you put your calculator in radians and plug in 2 pi over 3 and get the cos of it, it shall actually give you negative a half. And then if you plug in 4 pi over 3 in your calc, then get the cos of it, you also get negative a half. So this is what we end up having. So when you simplify this and calculate further, what we'll get is, so this times this will give us 1 over 8, this times this will give us 1 over 4. So we have positives right there. Then this minus that should actually be negative 3 over 4. But there's a minus sign here, so that means we're going to change that to a plus. So this and this will actually give us 3 over 8 plus 3 over 4. Now our final answer shall be equal to 9 over 8. Alright, so next let's look at a question, and this question is from UNEB 2001, and this was question number 16b. So we're being told to evaluate the integral of sine x sine 3x dx. So this is another unique example, but now in this case we have an example of a sine multiplying a sine, and we can actually see that there are double angles involved. So basically here we can basically see that we'll actually have to recall something from factor formula. So we're going to consider the following factor formula. So we need the factor formula that actually gives us a product of sine somewhere in it. So remember that whenever we had a cos A minus cos B, it always gave us a negative 2 sine A plus B over 2 sine A minus B over 2. So something in this format. So you can actually say there is a sine involved right here. But now the difference with this is when I compare that this is also sine, but there is no negative 2 right here. So what I'm going to do is I'm going to make this sine the subject and take the negative 2 to the other side. And how do I do that? I'm going to divide both sides by 2, actually by negative 2. And what I will have is negative a half cos A minus cos B being equal to sine A plus B over 2 sine A minus B over 2. So now this is basically what I want. So I can now easily compare with what I have right here. But now remember, as I emphasize in every single case, it is always better to compare A plus B over 2 to the bigger value. So I'd rather have this compared to the 3x. So I'm going to rearrange that. So when I compare, I'll compare sine A plus B over 2 sine A minus B over 2 with, now you've seen I've actually rearranged it into the form sine 3x sine x, because I want to compare this to the bigger value. But this doesn't change the meaning at all. So it's basically the same thing. So that means this is okay to do. Alright, so now let's compare. So when I compare, I'll say A plus B, I can actually say that A plus B is equal to 3x. So when I make A plus B the subject, A plus B shall be equal to 6x. And that shall be equation 1. So next, let's compare the other one. So A minus B, as you can see, shall be equal to x. And then if I make A minus B the subject, it shall actually be equal to 2x. And that shall be equation 2. So next, I now want to find the values of A and B. And one of the first steps we can do that is by first. So if I add equation 1 and equation 2, I can actually find the value of A. So when I add them, I'll actually see that 2A shall actually be equal to 8x. Then if I make A the subject, A shall actually be equal to 4x. Then to get B, I'll get equation 1 minus equation 2, which is going to be equal to 2B, which is equal to 4x. Then we shall say that B is equal to 2x. So now that I know what B and 2 are, I'm going to substitute them into the factor formula that we had actually derived. So I'm actually going to substitute it inside here right there. So I'm going to substitute for A and B. So now we'll have, so therefore negative a half cos 4x minus cos 2x shall actually be equal to sine 3x sine x. So therefore the integral becomes this. So now wherever this integral now shall actually become negative a half cos 4x minus cos 2x dx. So I can see that I can pull out the negative a half from the integral, and I'll be left with the integral of cos 4x minus cos 2x dx. And basically both of them can actually be solved using u-substitution individually. So what happens is when I integrate cos 4x, I'll actually get a quarter sine 4x, and then when I integrate cos 2x, I'll get a half sine 2x. All these in bracket. Now I can multiply the negative a half inside, and what I'll have is negative 1 over 8 sine 4x plus a quarter sine 2x plus c, and that is our answer. Alright, so that's it for this section. So let's look at another kind and another category. So let's look at questions where there is an integral of odd and even powers of trigonometric functions. So there are those of odd and those of even powers. But for the beginning, let's look at integrating even powers of sine x and cos x. So here we're going to remember trigonometric identities related to cos 2x. So this is actually going to be the foundation of this section. So remember from trigonometry that cos 2x is equal to 2 cos squared x minus 1. But actually has two different ways you can actually show it. So it can also be cos 2x is equal to 1 minus 2 sine squared x. So now let's look at what happens here. What if I actually make cos squared x the subject? I'll actually see it cos squared, we can actually first say that the first step is we can take the 1 to this side and to become a plus 1. So I'll have cos 2x plus 1 being equal to 2 cos squared x. Then cos squared x shall actually be equal to 2 cos 2x plus 1 over 2. So that's what I get right there. So I can also equally see that that if I also make try to make sine squared x a subject, I can actually see that first of all I can take this. Let's take this 2 sine x to this side, and then I'll bring this cos 2x to this side. So I'll have 1 minus cos 2x being equal to 2 sine squared x. And then if I divide both sides by 2, I'll have sine squared x being equal to 1 minus cos 2x over 2. So now I think you can see a different way to express the powers of cos squared x and the powers of sine squared x in terms of a double angle. So therefore we use the following trigonometric identities. Cos squared x is equal to a half times 1 plus cos 2x, and then sine squared x is equal to a half times 1 minus cos 2x, and these are going to be our formulas. So these are going to be our most important tool for solving those that actually have even powers of sine x and cos x. So let's look at a question. So in the first question, we're being told to evaluate the integral of sine squared x dx. So unlike other numbers, this one has to first be converted and put into the form of a double angle before you can actually integrate it. So let's look at it. So now we remember that what sine squared x actually represents. So remember from these even powers that actually represent sine squared x as a half times 1 minus cos 2x dx, as we've just seen. So next we can actually see that the half can be pulled out of that integral, then we remain with 1 minus cos 2x dx. And then this can actually be worked on. So this part alone can be worked on using u-substitution, but we can also see that the integral should actually be negative a half sine 2x, and then the integral of 1 is x, as you can see right there. So basically our answer, if we multiply the half inside, our answer shall be a half x minus a quarter sine 2x plus c, and that is the answer. So question number 2, we're being told to evaluate the integral of cos squared x dx. So this is basically the same. So we're actually going to remember that from even powers, as we've just seen, that cos squared x can actually be represented as a half times 1 plus cos 2x dx. So I can pull out the half from that integral, and this is what I'll have. Now next, you can actually see that the integral of cos 2x is actually going to be equal to a half sine 2x, and then this is actually going to be equal to x. So this is what I have right here. And then if I multiply the half inside, we shall have a half x plus a quarter sine 2x plus c, and that is our answer. Alright, so question number 3, we're being told to evaluate the integral of cos squared times, in bracket, 3x plus 1 dx. So what are we going to do in this case? So basically in this case, it's also the same thing. It's just that this 3x plus 1 represents the angle involved. So what happens is it's actually exactly the same thing. So remember as we've still said that this cos squared of, if cos squared of x is equal to a half times 1 plus cos 2x. So what you can basically see here is the angle that you actually have here is the angle that you keep right here. So since our angle right now is 3x plus 1, that means we shall have this as a half times 1 plus cos 2 into bracket. Now we shall have 3x plus 1 in this case. So that's the only difference. So now basically when I integrate, actually I can see that these two can actually multiply inside, and then I'll have cos 6x plus 2, as you can see right there. And then this can actually be worked on. So actually I can see when I integrate 1, I'll actually get x. Then when you integrate this cos 6x plus 2, so this will actually work out using u substitution. So you let u be equal to this 6x plus 2 and work it out. But as I always tell someone that this is actually a alright, so if you use u substitution, this will actually be easy to solve and it will actually be clear. But I can already see directly at the integral of this cos 6x plus 2 is going to be equal to 1 over 6 sine 6x plus 2, and that's what we're going to have. So when I open those brackets, I'll have a half x plus 1 over 12 sine 6x plus 2 plus c. Alright, then next we're being told to evaluate the integral of sine squared 2x. So this is like the square of a double angle. So what do we do in this case? So as you can see that the angle involved is also right now going to be equal to 2x. So this is actually basically the same thing as you've just seen in the former number. So that means right now sine squared 2x shall actually be equal to a half into 1 minus cos 2, but the difference is the angle shall actually now be equal to this 2x the way it's actually given. So basically 2 times 2x is going to be equal to 4x. So we now have the integral of a half times the integral of 1 minus cos 4x, of which we know that when we integrate 1 we'll get x, and when we integrate cos 4x we'll get a quarter sine 4x plus c. So as I will always say, I just chose not to show everything in this case, but this can actually easily be worked out using u substitution, where you let u to be equal to 4x and to actually solve this for you. So basically I can already say that this will actually give me a quarter sine 4x. So when I multiply the half inside, we have a half x minus 1 over 8 sine 4x plus c. Alright, so question number 5, we're being told to evaluate the integral of sine squared x over 5 dx. So the difference here is you can actually see that the angle now is x over 5. So that simply means that now this is what we have. So just have a half into the integral of 1 minus cos 2, and then the angle right now will be x over 5, as you can see, dx. So now multiply the 2 inside, I'll actually have a half into the integral of 1 minus cos 2x over 5. So what happens when I integrate this? So just use u substitution, but now you'll get the answer as negative 5 over 2. Actually, you get 5 over 2, positive 5 over 2 sine 2x over 5 as your answer. So when I multiply the half inside, I'll have a half x minus 5 over 4 sine 2x over 5 plus c. Question number 6, we're being told to evaluate the integral of sine power 4 2x dx. So now the difference here is now this is actually to the power 4. So when someone looks like this, it actually looks scary at the very beginning, but this is actually a very easy number to work with. So remember that power 4 simply means that we're squaring a value that is already squared. So what does that mean? So that means that we can actually see that this is like the square of sine squared 2x. So that's basically what it means. So we're going to have, so where there is sine squared 2x, we can actually represent that. So this is actually going to be equal to a half into 1 minus cos 2 times 2x, and then we're going to square everything because everything is now originate to the power 4. So when we square this, we can actually see that a half squared shall actually be equal to 1 over 4, and then this bracket here shall actually be squared. So when we square this bracket, you can actually see that when we open it, actually we can take the 1 over 4 outside the integral, and that's why we have it here. So when we open this bracket, 1 minus cos 4x squared will actually get 1 minus 2 cos 4x plus cos squared 4x dx. But as you can see, now we have another power involved, this cos squared 4x. So this also needs to be converted in the form of a double angle. But we can actually see that cos squared 4x shall actually be represented as a half into 1 plus, now remember it will be 2 into 4x, which is 2 times 4x, which is 8x. So that's what we'll have. We'll have it as a half into 1 plus cos 8x. So we're going to substitute that back in, and this is what we'll have. So basically I can set, I multiply this a half in, and then I'll have a half plus a half cos 8x dx. So now when I integrate all those terms, I can see that the integral, when I integrate 1 I get x, when I integrate 2 cos 4x I get positive 2 over 4 sine 4x plus, so when I integrate a half I get a half x, and then when I integrate a half cos 8x, what I get is 1 over 16 sine 8x plus c. And therefore, when I multiply this a quarter in, I get x over 4 minus 2 over 16 sine 4x plus 1 over 8x plus 1 over 64 sine 8x plus c. Then therefore, if I collect like terms, when this adds to this, I can see it sometimes combined together. Then all I'll have is 3 over 8x minus 1 over 8 sine 4x plus 1 over 64 sine 8x plus c. And that is the answer. So question number 7, we're being told to evaluate the integral of 1 over sine squared x times cos squared x dx. So how do you solve this question? Now this is slightly different from the rest. So this one may not be a direct substitution. So this one will actually require some kind of understanding, but this is actually going to be easy also. So this is what we have. So now the first step we can actually see is that sine squared x, cos squared x all have the same power, so you can combine them together and square them together. So you can have it as 1 over sine x cos x, then square that. Then we remember something from trigonometry, that sine 2x is actually equal to 2 sine x cos x. So we're going to use this other understanding of double angles, so where we actually have a sine 2x involved. So remember sine 2x is 2 sine x cos x. So when I make sine x cos x the subject, it's actually going to be equal to a half sine 2x. So I'm going to replace these with that. So now basically what I'll have is the integral of 1 over a half sine 2x and then square that. So when I square that, what I'll have is 1 over, so the square of a half is a quarter, and then I'll have sine squared 2x. Now I also know that 1 over sine squared 2x is the same as cos x squared 2x. So I can actually convert that into a cos x squared 2x over a quarter. But now remember, having this divide by a quarter is actually going to be equal to 4. So that means, because if I have anything divide by, let's say, okay, so we have cos x squared 2x times, actually divide by 1 over 4. So remember that when we change this into a multiplication sign, I'll have it as 4. So it will be like cos x squared x times 4. So that means what I'll end up with is 4 cos x squared 2x. So now the next step I can see is that I can actually let u to actually be equal to 2x. And why is that? It is because the integral of cos x squared of something is actually exists, so I can actually do that. So we can say that du dx is actually going to be equal to 2, and then if I make dx subject, dx should actually be equal to 2 du over 2. So therefore this is what I'll end up having. So I have 4 cos x squared u times du over 2. So I can see that this and this can reduce, and I'll be left with a 2. So 4 divided by 2 is 2. So I have 2 into the integral of cos x squared u. So now the integral of cos x squared u is known. It's going to be equal to negative cot u plus c. So I have 2 times that. So, but remember that u is 2x, so therefore I have 2 into negative cot 2x plus c. So when I multiply it in, I end up with negative 2 cot 2x plus c. And that is the answer. Alright, so let's look at another question. So this looks almost similar in arrangement to the former question, but it is actually very different. So we're being told to evaluate the integral of 1 over sine x times cos squared x dx. So how do we solve this one in this case? So as I've said, it's different from the initial one, but it's also possible to work out. So in this case, the first step, we can actually see that where we can see what we're going to do is convert this. So remember that 1 over cos squared x is actually the same as sec squared x. So we're going to have it as sec squared x over sine x dx, like that. Next, we remember that sec squared x is actually the same as 1 plus tan squared x dx. And then I can see that I can now split this into 2 different integrals. So I'll have 1 over sine x plus tan squared x over sine x. And this is okay, that's correct. And then basically what I can see that the next step is I can convert this tan into the form of sine and cos. So what will I have? So I'll have sine squared x. So tan squared x is actually sine squared x over cos squared x. Now we will have them dividing this sine x, as you can see right there. But now that division sign, if turned into a multiplication sign, is going to be equal to 1 over sine x, of which you can see that this and this will reduce, and then I'll end up with the integral of 1 over sine x plus sine x over cos squared x dx. So now this is going to be easy to work out. So now I'm going to separate these into two different integrals, of which we're going to solve them. Now, as I can already see here, this is actually going to be easy because 1 over sine x is actually cosec x, so this shall actually be easily integrated. Then right here I can actually say that we shall actually use u-substitution, where we make u to be equal to cos x, and then we'll get a value which will cancel out with this sine x, so everything will now easily be worked out. So as you can see, 1 over sine x is cosec x, and then this remains as sine x over cos x. So let's solve for each one individually. So for the integral sine x over cos squared x dx, I'm going to let u to be equal to cos x, and then du dx is equal to negative sine x. So if I make dx subject, dx shall to be equal to negative du over sine x. So therefore, if I substitute everything back, so where there is dx, I actually put this, I'll have this sine x over u squared times negative d over sine x. So this and this will cancel, and we'll have no x values left, which means we've actually chosen the right value to make u. So I'll have negative into the integral. Of course, this can be converted as u to the power negative 2. So the integral of that is going to be equal to u power negative 1 divided by negative 1, which is actually the same as negative u to the power negative 1. I mean, it's actually negative 1 over u, but because of this negative on the outside, I'll have a positive 1 over u plus c. But remember that u is cos 4x, so therefore our answer for this is 1 over cos x plus c, which is actually the same as sec x plus c, because 1 over cos x is sec x. So for the other side, for the integral of cosec x dx, so remember earlier in this section, I'd actually shown you a method to actually integrate this cosec x. I told you it's quite different because of what we actually have to select for u. But we remember the answer we got was ln cosec x minus cot x plus c. So therefore we have the integral of 1 over sine x times cos squared x dx should actually be equal to ln cosec x minus cot x plus sec x plus c, and that is our final answer. So question number 9, we're being told to evaluate the integral of 1 over cos squared x times 1 minus tan x, and then we actually have that 1 minus tan x being squared. So how do we do this? So this is also an easy one. So the first step is we can actually see that we're going to let u to actually be equal to 1 minus tan x. And why is that? It is because when you actually integrate this tan x, it should actually give us a value that will allow us cancel out this cos squared x along the way. And that is because this tan x can actually give us a sec squared x somewhere, of which that is in a way related to cos squared x, but you see that in the calculation. So remember, du dx should actually be equal to negative sec squared x, of which negative sec squared x is the same as negative 1 over cos squared x. So I think you can now see where we're going. So if we make dx the subject, dx should actually be equal to negative cos squared x du, as you can see right there. So now if I substitute everything back, this is what I'll have. So I think you can now clearly see that this and this will be eliminated, and then I'll be left with the integral of negative 1 over u squared, of which I know that this is the same as integral of u to the power negative 2, and then the negative will go outside. So the integral of that is u to the power negative 1 divided by negative 1. But remember, because there is this negative here and this negative here, that this will become a positive. So I have a positive 1 over u plus c. But remember that u is 1 minus tan x. So therefore we have 1 over 1 minus tan x plus c being our answer. And that's what they wanted. So question number 10, we're being told to evaluate the integral of 1 over cos 2x plus sine squared x dx. So what's different in this question is actually I can see that one of them is a power. So this is sine squared x, and this is actually a double angle. So this is cos 2x. But good enough is we know how to convert this double angle into a power also. So what happens is, in this case, I can actually see that inside this cos 2x, I can actually get a value that has a sine squared x involved, which I'll combine with this and to allow me to easily solve this number. So remember that cos 2x from trigonometry is equal to 1 minus 2 sine squared x. So I'm just going to substitute that. So the integral becomes 1 over 1 minus 2 sine squared x plus sine x. Now, negative 2 sine x plus sine squared x is actually going to be equal to negative sine squared x. So I have the integral of 1 over 1 minus sine squared x dx. But also from trigonometry, we know that 1 minus sine squared x is actually cos squared x. So I have the integral of 1 over cos squared x dx. And then the integral of 1 over cos squared x dx shall actually be equal to the integral of sec squared x, because 1 over cos squared x is sec squared x. So the integral of sec squared x is tan x. So I have tan x plus c as my final answer. Alright, so next we look at odd powers of trigonometric functions. So now this is where we have odd powers involved. But this part is also in a way comparison to actually what we've just done before. There's just a slight difference. So under this, we're going to use the following trigonometric identities. So we're just going to use a basic knowledge of what we already know from trigonometry to actually work out these ones. So we remember that cos squared x plus sine squared x is 1. So this is going to be useful. Then you just need to remember that 1 plus tan squared x is equal to sec squared x. And then you need to remember that 1 plus cot squared x is equal to cos sec squared x. So you ask yourself, how will this be useful? Because I don't see odd powers involved. But I'll tell you, these will actually make basic sense as we look at different examples. Let's look at an example. So just trust me on this one. So let's look at an example. So we're being told to evaluate the integral of cos cubed x dx with respect to x. So you ask yourself, how will this help? It will actually help us in a big way. So what we're going to do is we're going to first convert this into a way where we actually have an even power involved. So you know that cos cubed x is the same as cos x times cos squared x dx. So we're going to first put it in that format, and remember that is true. And then we can see that cos squared x is actually, so if we look at this, we can actually set, if we make cos squared x subject, it's actually going to be equal to 1 minus sine squared x from there. And then I can already see that there is a value inside this sine x here that I can get that will eliminate this cos x. So the next part is going to be to introduce u-substitution. So we're going to let u to be equal to this sine x, of which du dx should actually be equal to cos x. And I think you can see that we shall now have a value that will cancel out that other cos x. So if we make dx subject, dx should actually be equal to du over cos x, of which put that back, and you can actually see that now this cos x will be cancelled, and you'll be left with the integral of 1 minus u squared du. I think you now get the point. Now the integral of this, we know that when you integrate 1 we have u, and when you integrate u squared we'll have u to the power 3 over 3 plus c. But remember that u is sine x, so therefore we have sine x minus a third sine cubed x plus c, and this is our answer. So it's actually as simple as that. Alright, so next, what if we have to evaluate the integral of sine cubed 2x dx? What do we do in this case? So it's basically the same thing. So you know that sine cubed 2x is actually the same as the integral of sine 2x times sine squared 2x dx. Then also from trigonometry, we know that this sine squared 2x should actually be the same as 1 minus cos squared 2x. And then I believe that there is a value inside this cos 2x that can actually eliminate this sine 2x. So we're going to let u to be equal to cos 2x, of which du dx should actually be equal to negative 2 sine 2x. And then dx, if we make it the subject, should actually be equal to negative du over 2 sine 2x. And then when I put that back in, clearly you can actually see that this will actually eliminate this sine 2x, and I'll be left with this. Actually, you can see that here we have a negative half. We can actually pull out of the integral, so have negative half into 1 minus u squared, of which we will have it as negative half into u minus u cubed over 3 plus c on the outside. But remember that u is cos 2x, so therefore we'll have this. Now multiply the negative a half inside, and we'll have negative a half cos 2x minus, actually we'll have a plus now because it was a minus, plus 1 over 6 cos cubed 2x plus c. And this is our final answer. Alright, so in question number 3, this is actually now slightly different. So being told to evaluate the integral of cos to the power 5 3x dx. So now this also looks scary for some, but this is also an easy one. So what do we do in this case? So you know that cos 5 to the power 3x, so we need to just make sure that there are some even powers involved as we calculate this. So what we're going to do is, you can see that this can actually be represented as the integral of cos 3x times cos to the power 4 3x dx. But now you also know that this side here can also be represented as the square of a square. So it's actually the same as cos squared 3x and then we have the square on the outside. So that's basically the same thing. Then we can actually see that this cos squared 3x can actually be represented as 1 minus sine squared 3x. And then now we can see that there's a value inside sine 3x that should actually help us eliminate this cos 3x. So we're going to let u to be equal to 3 sine 3x, du dx should actually be equal to 3 cos 3x, and then if we make dx subject, dx should actually be equal to du over 3 cos 3x. So put that back in and you can actually see that clearly. Now this will actually be eliminated, and then we'll be left with we'll have this a third, because we have this 3 here, so we can pull out a third, and then what we'll be left with is 1 minus u squared, and then the bracket squared. So when you open this square of the bracket, we'll have 1 minus 2u squared plus u to the power 4 du. So now that will become, so when you integrate that, for 1 we'll have u, and then for this we'll actually have 2 over 3u cubed, then for this we'll actually have 1 over 5u to the power 5. But remember that u is actually equal to sine x. So that's what you have to remember. Then multiply the third back in after substituting. Forever there is a u, put sine 3x. So we'll have a third sine 3x minus 2 over 9 sine cubed 3x plus 1 over 15 sine to the power 5 3x plus c. And it's as simple as that. Alright, so let's look at a question from UNEB 1997, and this was question number 2. So we're being told to evaluate the integral of tan cubed x dx. So this is slightly different from the former ones in that we don't have sine and cos directly involved, so we have a tan. But good enough, there is a relationship between a sec and a tan. So that's what we're going to be using mainly in this section. So now the integral of tan cubed x, how do we do it? So the first step is we know that this can actually be represented as tan x times tan squared x dx. But also, now we're going to convert this tan squared x now into the form of sec squared. So that's going to be the next step. It's because now we know that tan squared x is actually the same as sec squared x minus 1. So we're going to be using the knowledge of the relationship between a tan and a sec, actually, and a sec squared. So basically, when we open these brackets, we'll have tan x sec squared x minus tan x. So now I can say that I can actually split this into two different integrals that will be worked out independently. So now I believe we've seen how to work out this in the beginning of the section, and then now this is the one that we actually mainly have to look at. So let's deal with that. So as I can see this, I can already see that there is actually a relationship between a tan and a sec. So what I actually see is if I make a u to actually be equal to tan x, and then if I differentiate that, I'll get sec squared x somewhere. And I believe that will help us eliminate this sec squared x right there. So we're going to let u to be equal to tan x, and then du dx is equal to sec squared x, and then if I make dx subject, dx should actually be equal to du over sec squared x. So plug that back in and I'll have the integral of, so there is tan x, I put u sec squared x times this, so I have times du over sec squared x. So as you can see, as I've said, this will actually cancel out with that, and I'll be left with the integral of u du. So that means that was actually the correct substitution. So if I integrate that, the integral of u is u squared, it will actually be equal to a half u squared plus c. But remember that u is tan x, so therefore it means a half tan squared x plus c. How about the integral of tan x dx? I think we've already worked on this at the beginning of this section, but remember that what we had to do was to convert that tan x into a sine x over cos x dx, and then we can actually use u substitution. We're going to let u to actually be equal to cos x, and that's because there is a relationship between the derivative of a cos x and a sine x. So when we let u to be equal to cos x, du dx should actually be equal to negative sine x. So if I make dx subject, dx should actually be equal to negative du over sine x. So therefore, when you plug that back in, we'll have sine x over u times negative du over sine x. And then therefore what I'll have is this. As you can see, this and this cancel, and I'll be left with the negative 1 over u, of which I can take the negative out of the integral. Then the integral of 1 over u is actually ln u, so I have negative ln u plus c. But remember that u is actually cos x, u is cos x, so therefore I'll have negative ln u cos x plus c. So therefore the integral is tan cubed x dx being equal to a half tan squared x minus ln cos x plus C. So there are two different ways of expressing this answer. I just chose not to simplify this even any further, but actually I could have made this negative power negative 1 here, and I would have a 1 over cos x, which is actually equal to sec x. So actually this could have been a positive ln sec x plus c. So this could actually, the answer could also be a half tan squared x plus ln sec x plus c. But anyhow, both answers are actually correct and all of them will be marked. Alright. Question number 5. So we're being told to evaluate the integral of sec x tan cubed x dx. So good enough, there is a relationship between a sec x and a tan cubed x. So what do we do in this case? So the first thing we can actually see is this can actually be rearranged this way. So let's rearrange it as tan cubed x sec x. So we know tan cubed x can actually be represented as tan squared x times tan x, as you can see right there. But now we also know that there is a relationship between a sec squared x and tan x sec x, as you can see right there. So the next step is going to be to convert this tan squared x into the form of sec squared x minus 1 being equal to that. So now I know there is a relation between a sec x and tan x sec x. So we're going to let u to be equal to sec x, because the derivative of sec x will actually give us a value that will cancel this section right here out. So du dx should actually be equal to tan x sec x. I think you can see what I mean, because the derivative of sec x is this. And then if I make dx subject, dx should actually be equal to du over tan x sec x. So plug that back in, and this is what I end up having. So we have sec x, we actually put there u. So we have u squared minus 1, then times tan x sec x times, well, so we replaced for dx and we've actually placed the value right here. So now we have du over tan x sec x. So you can actually see that this and this will be eliminated, and we'll be left with the integral of u squared minus 1 du. So when you integrate that, we'll have u cubed over 3 minus u plus c. But remember that u is sec x, so therefore we have a third sec cubed x minus sec x plus c, and that is the answer. Alright, so next I have an exercise for you that I encourage you to try out. So if you can solve these integrals and get the answers that I'm showing you on the right hand side, I believe that you have a firm understanding of what we've covered in these integrals of trigonometric functions. So try these numbers out and compare your answers to the answers that I have on this right hand side of each one of them. So these ones are question 1 to question number 5, and then they continue. So next we have question number 6. So this is question number 6, and that is its answer. Question number 7, and that is the answer right there. So we have question number 9, and that is the answer right there. And lastly, there is question number 10, and that is the answer right there. So try this out. This will test your knowledge of what we've learned from the beginning of this section, and I believe that after this you'll actually be very good at your knowledge of integration of trigonometric functions. Thank you for watching. Thank you so much for watching this video. I hope the video really helped you. If you did, feel free to tell me below in the comments. I'll make sure to get time to read through your comments and to reply to you. And also, if you're new to this channel, I encourage you to join the community by subscribing, and then make sure to hit the notification bell so that you get updated every single time I upload a new video. Again, my name is Emmanuel Olega. Thank you so much for watching. See you in my next video.